In this video we're going to look at Newton's solid of minimum resistance. So the idea here is that if we had a bullet, say, so let's draw the base of the bullet, it looks like that, and the bullet's travelling in kind of that direction. Now the question is then, what shape do we have to make the top of the bullet in order to minimise resistance? Now if we make it just like a cylinder like that, there's going to be a huge amount of air resistance against this bullet, so you wouldn't design a bullet like that. So common sense tells us that if you were to curve the surface, the top of it in some kind of arc, then that's going to minimise or reduce the resistance. So there's the air travelling and hitting the bullet. So really the question is, what's the shape of this curve that's going to minimise this resistance? So if I put an x and y coordinate in, so we could call that our x, we can call that our y, and that's a 0 point. So we're just saying, what's the shape of this curve? Okay, so now kind of common sense tells us well that if we had the surface, okay, so if the surface was completely circular, okay, and that's the direction of travel, then we're going to have all the air is going to be hitting that there, so they're going to have a maximum air resistance. Now if that was in this position here, then the amount of air resistance would decrease, okay, and if we were to shape that here like that and fire at this direction here, then the air resistance is going to be a minimum. So the air resistance, you can see coming in here, that shape has got a little effect in it, it just flows over the top. The air resistance here, there's greater air resistance, and this surface here has got an even greater. So the area that is open to the airflow is going to give us the maximum resistance, and the area that's closed to the airflow is going to give us a minimum resistance. Okay, so really what we're saying then is, if we were to look at the top of the bullet and it was like some curve like that, then the direction of travel of the bullet is this direction. Okay, but if we take the normal to the surface at that point here, so the normal is sitting along here somewhere, and what we're really interested in is what it would be the normal component of this velocity. Okay, so there's the bump, 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 bump. That's the normal component here. Okay, now if we were to go right to the very top of the bullet, then the normal would be sitting up here, and the normal would be in the same direction as the velocity. Now that's the same as what we have here. Okay, if it was opened up to the airflow completely, then the normal is in this direction and the velocity, so the normal is in that direction and the velocity is in that direction. So we'll have a maximum resistance at the top, and if you were to come way around to the side here, then the normal would be in this direction and the velocity would be in that direction, and that would be the same as what we've got up here, where the normal is sitting at 90 degrees. That's the normal, sitting at 90 degrees to the velocity. Okay, so what we're interested in is as far as the air resistance is concerned, is not the actual, it's not, if we say that the air resistance is directly proportional to the velocity squared, okay, so that's an assumption we're going to make, then what we're interested in is not the direct velocity, we're looking at the velocity that is normal at each of the points on this curve. Okay, so given that, what we can do is we can say then that we know that the air resistance is going to be directly proportional to the velocity squared. Okay, so I'll just call it AR. Okay, so AR is, I'll just put equal. Okay, so it's directly proportional, but there'll be a constant proportionality, but we'll leave it equal at the moment. So it's equal to velocity squared, but again it's not the velocity, it's the normal component of that velocity at each of the points. Okay, so the normal component, how are we going to get the normal component to that velocity? So if we were to draw the curve for the top of the bullet, and we were to draw our x and y axis like that, so we pick a point here and we find the normal. So there's the normal there. So the normal there is going to make this angle phi. So this angle in here, okay, that's going to be equal to our pi minus phi. Okay, so we'll get the normal component by taking the cosine of this pi minus phi, but it's not the cosine, it's going to be the cosine squared. Okay, because it's direct proportional to the v squared, not the direct proportional to v. So it means that the air resistance is just going to be equal to v squared cos squared pi minus phi. Okay, again, this cos, it's just like taking a dot product. We're looking for the component of one vector in the direction of another. Okay, so and the vector is the normal vector, so it's only got length 1. Okay, so it's the component of that normal vector there in the direction of the velocity, okay, which is this little vector here. Okay, and we're doing it for each of the points along the curve. Now, what we've done there is we've found the air resistance at this one point here, but of course the bullet is a three-dimensional shape. Okay, so what's going to happen is if we take it round like that, then the bullet's going to curve. That's the shape of the bullet. So we've in effect just taken a section across the top of the bullet. Okay, and that's you looking down onto that circle. Okay, so that same air resistance is going to exist at every point along that circle there. So the circle is going to have that radius is going to be, or the circumference is going to be 2 pi times the value of x, where x is just going to be that distance there, which is going to be in effect a radius. Okay, so that there is going to give us the air resistance around that loop. Okay, now what we have to do then is we're not just looking at the air resistance around that loop because it's curved. Okay, so it's a three-dimensional shape. So what we want to do is we want to take that loop that we've just created, and if we were to look at the top of the bullet, so we look at a curve of the bullet, so that's one small infinitesimal part of the curve of the bullet, then we could drop our perpendicular down and we'll just end up with this little distance here is going to be dx, the little distance up there is going to be our dy, and this little shape here will be our ds. Okay, so what we're going to do then is we're going to take this, which is the air resistance, and we're going to integrate it v squared cos squared pi minus phi times 2 pi x, and we're going to integrate it with respect to our dx. Okay, so as dx changes, dy changes, and our value for our ds is going to change as well. Okay, so that there is going to give us our air resistance. Okay, and that's our little equation. That's actually what's derived in the book there as well. Okay, the only difference in the book that this dx is replaced by the value of ds cos phi, which is, if this is angle phi in here, okay, this little angle in here is phi, then dx upon ds equals cos phi, so you can say dx equals ds cos phi. So he's just got a ds cos phi in there. I've just replaced it with straight with the dx. Okay, so what we want to do then is we can rewrite that, because we can notice a wee bit of geometry, we know that from what we've done previously, we can write that if we look at the Pythagoras theorem in terms of differentials, we can say that's dx squared, that's dy squared, and that's dz, well, we call that ds, okay, ds squared. Then we can say that our dx squared plus dy squared equals ds squared, divide by throughout by dx squared, we'll have 1 plus, now that will be dy squared upon dx squared, so I'll just call that y derivative squared, okay, it's just going to be equal to our ds upon dx squared, okay. So I could find the reciprocal of this here, so I could write that as dx upon ds squared, which will equal 1 upon 1 plus y derivative squared, okay. But dx upon ds, if that's the angle phi, dx upon ds is just going to equal cos phi, okay. So dx upon ds is going to be our cos phi, okay. So let's see, we've got all this right. So we've got dx squared, dx upon ds squared, that would be dx by ds squared, so it would actually be the root of all of that, so it would be the root of that, okay, because I've missed out the square term there, okay. So if I've taken the reciprocal and I've square rooted one side, okay, so that's going to equal cos phi. So you could then say, if you wanted to put it down, you could say cos squared phi would equal just the square of all the other side, which is 1 plus y derivative squared, okay. So we're going to use this little fact here, and that's quite a handy little bit of geometry, and you can do the same for your sine and your tangent as well if you want, and see what you end up with, okay. So what we can do is we can rewrite the equation up here. Now the v squared is just going to be a constant, 2 pi is going to be a constant, so we can take them out. Cos pi minus phi is the same as minus cos phi, okay, so we can then take these out, so we're going to end up with our, it would be minus v squared times 2 pi, and it would be integral of cos squared phi times x dx, okay. And again, it's from 0 to x, okay, where 0 is just the area up to your top of your bullet, your 0 point is just the centre of the bullet, and your x is this radius of the bullet, okay. So let's see where we go here. Now cos squared phi can be replaced by what we have above here, and these here, we'll leave these out because we can always just multiply them in at the very end, okay. So you just end up with the integral from 0 to x of our 1 upon 1 plus y derivative squared, and it's all times x. I'll just put the x up the top line, so it's x times dx, okay. So that there is what you want to minimize in order to ensure that the air resistance is a minimum, okay. So what we can do then is we can use a calculus of variations to do that, and we can notice that we can simplify it here, the Euler-Lagrange, to partial f upon partial y derivative equals a constant, okay, because this is a function of simply the y derivative. It's not a function directly of y, okay. So we then to go through that differential, that's like saying partial by partial y derivative of x times 1 plus y derivative squared to the power of a half equals a constant. So the x is a constant, looks like a constant here because it's partial differentiated with respect to y. So we got x times, and it's going to be a half of 1 plus y derivative squared to the minus a half, and differentiate plus a differentiate inside this times 2 y derivative equals a constant. Okay, so the twos cancel out, and you're just going to be left with x y derivative upon 1 plus y derivative squared, and that is, because I've taken it down, so it's squared, all squared from this point here is equal to a constant. Okay, so what we do is we solve this, and the solution that's given is a parametric solution. So I'll continue, I'll write that in the next page, and we'll continue, we'll get that parametric solution done. Okay, so let's go up here, and I'll rewrite that out. It's going to be x y derivative upon 1 plus y derivative, we bracket squared, all squared equals a constant. Okay, so we'll go to that point there. Now what we do is we say we'll let y derivative equal some value p, and we'll leave that constant there as just as a c. So we put a p in here, okay, and then we'll rearrange for x. Then you're just going to end up with x will be c divided by the p, c upon p, and it'll be, this will come up, so it'll be 1 plus p squared, and it'll be all squared as well. Okay, so that's what the value for x is. Okay, so the y value, well, y is just going to equal, well, we just integrate this here, so y is going to be integral of p dx. Okay, so just from here, y derivative is p. Okay, so y will be the integral of p dx. Okay, so what we could do then, a little bit of jiggery pokery here in order to get this into the right format. We can say then that if we were to rewrite this, we could rewrite this as our dx. Dx would equal, well, it would be c upon dp 1 plus dp squared all squared. Okay, so then we can rewrite this equation here, and we can put this here in for the dx. Okay, so you'll have a y will equal the integral of p times, well, that's going to be c upon dp, and that would be 1 plus dp squared all squared. Okay, so that could be rewritten as, we could take them out as separate. Okay, so we'll square these out and take it out separate. Okay, this doesn't show you this in the book, so I had to sit down and figure this out. So we could say one part I will just call y1. Well, the first part is going to be the integral of c times p, right? And when we square this out, the first term is just going to be our 1. Okay, so we just got our dp, and this thing here is just the 1. Okay, so that's going to equal minus c log of p. So c is a constant, and it's p of n dv, the integral of that is minus log p. Okay, so that's the first part of it. Second part of it is the integral of cp upon dp, and when we multiply this out, it's going to be the 2dp squared. Okay, so that is equivalent to the integral of 2cp dp. Okay, just cancelling out the dp's, which equals it's going to be 2 at the top and cancel out the 2, so you're just going to end up with cp squared. Okay, so that's the second part there. So the first part there, second part there, and the third part there is just an extension of what you've got above. So that's y3 is going to equal, well, it's the integral cp upon dp of dp. Now it's got to be dp to the 4. Okay, that's that squared out, and that's going to equal, well, by what we have above, if you follow the same route we have above there, then we're going to have the that term 3 upon 4p to the 4. Okay, so convince yourself of that. You can convince yourself of that if you work through this integration here. Then this integration here is of the same type, but it's just raised to the power of 4, and there's no factor of 2 in, so you work through it, you'll get 3.4 p to the 4. Okay, so we're going to end up with, in the end, y is going to equal, well, there's our constants of integration, but we've no put in above, so we'll just add them in. So that plus our factor of c there as well, actually, that c is still in here. We're going to have c, and we'll have minus log of p plus p squared, and it'll be plus 3 upon 4 p to the power of 4. Okay, so that's what our y part of the equation we're looking for. Okay, so the parametric equation. So, and the x part, we've already worked out the x part. X is c upon p, 1 plus p squared all squared, c upon p 1 plus p squared all squared. Okay, so these here are our parametric equations of the Newton solid of minimum resistance. Okay, so what we'll do is we'll go and we'll look at it in a graphical calculator. So let's have a look and see Desmos, see if I can find it. I've already popped this in. Okay, so I've just put in these values, this equation into Desmos. I've kept c in a at 1. Okay, and you can see when I vary p, there's it maps out the shape. It only does it for 1/2. Okay, right, it only does it for 1/2. So, but the other half would be symmetric. Okay, so it would just be symmetric along there. So you can see it mapping out this little curve here. Maybe zoom in a bit. Oh, well, that really matters if you zoom in. So you can see that curve it maps out. That curve should be a curve of minimum resistance. Now it turns out, although I've not covered all the work myself, that's not necessarily all that accurate to reality. Now what I've done is I've put in a, well, that's a bit strange there, I noticed that coming out. That's alright, that's fine. Okay, right, so I've put down a link below to a fuller description of this, an excellent bit of a nice bit of work by a guy called Qing Hui, And it looks like a project he's done back 2006. So there's a note down below where you can go and download that. I will work through it myself as well because this all looks quite interesting. But that gives you a kind of lead in to that problem, and it's one of the problems that's in the book there that we're working through. Okay, so thank you for listening, and goodbye.